you already heard, I'm at UCSD. I started in the Supercomputer Center in 2001. This is going to be my 25th year this year. And a couple of years ago, around 2018, we started a department, data science department, with its undergrad and graduates. And over the last 2 years, there was an effort to merge actually SDSC and HTSI, keeping their identities, but under a school, to see how a research organization can be a part of the education fold here. So it's an experiment happening at UCSD. We'll see where it goes. But my work also over the years evolved a lot. I started as a computer scientist, and at some point I got called a data scientist, but my background is actually in computing and workflows and integrating the breadth of science. And that breadth of science led me to different areas that we end up integrating those workflows into platforms or solutions that many users from different backgrounds use. So, but there's always that cutting edge science and technology integration, and more in ways that benefit the society. So, and we are solving problems. We have an approach to solve problems, but it doesn't have a name yet. And I think the society needs it. So over the last year, I decided to merge everything we do. We had a Convergence Research Institute for training in problem solving, cross-disciplinary problem solving. We had the Wi-Fi program, which became a 50-person lab over the years. And then we had the Workflows for Data Science Center of Excellence. So what we ended up is merging these under this new lab identity to do more problem solving with different communities. So at the heart of our approach in that sense is this use-inspired problems to understand with our partners from the beginning, including the expertise, to understand what would be useful to do. And we really look for the state of the possible with science and AI, and then turn those integrated things into an innovation pathway to build something usable. So it's sort of a proof of concept. And then since we started with partners, they become our scale and sustain partners as well. So we create the partnerships to create those as scalable solutions that integrate into the societal systems that they need to be integrated into. And the choice of double infinitum is right for the analogy, so to say, because it's endless work, right? And the problem is, the more, and the opportunity, and actually the good problem is, we learn more as we scale things. And since the science and technology evolves as well, as we learn more details about what we need to do, the more integration happens and the more innovation pathway happens. We noticed over the years, this model has been actually really successful in the type of things we are trying to do. So even in our cyber infrastructure building now, we apply this, very use-inspired. So in terms of computing research areas, what this ends up being, we start with definitely the integrated research workflow backdrop. But over the years, we needed more and more systems that don't really fit the mold of scientific computing. So that's where this composable systems context came to. And we were able to influence NSF actually to do some investments there, National Research Platform, and like more Kubernetes managed systems expands, and edge computing with SAGE. So there's a whole continuum of systems actually in the national cyber infrastructure now we can compose at the digital continuum and run services on. So instead of doing system integration, we do capability integration in these workflows through services. And that also helps us to bring big data and knowledge systems into it, so we can integrate dynamically, urgently available services with data and knowledge systems. And turns out, actually, these are the ingredients also for digital twins and AI, in terms of especially agentic AI applications in applications for both science and also the systems that support the science. So those are our current focus areas. And the idea is, can we harness everything that is available to generate impactful solutions? And that's what we define societal computing. So we don't do any solution in that sense. It has to have cutting edge science and technology into it, so it makes sense to create an innovation pathway. That's what the tech industry calls deep tech. I think it's called R&D actually. So there is sort of a tongue-in-cheek in a way. There are equivalents of this in the industry as well. And this sort of is about making that complex, deep issue simpler, right, through convergence, composable computing, including workflows and services and data systems, but also doing things we don't normally do, like co-design and co-production, multi-sector partnerships. So how do we actually create an innovation ecosystem, or in a way that by building systems that support that innovation ecosystem? The lessons learned for this happened for me. I fell into it, so to say, because I was always interested. My brain works with integrating things, right? I have to put it into pieces and put those pieces together, sort of break it better context there. And workflows is a natural thing for me to work on in that sense, and services. But then over time, in 2008, in the aftermath of the 2 fires in San Diego, the writing was on the wall. We had a sensor network. We become quite a testbed for fire environment data. And, we were doing fire simulations. So bringing those together and closing the loop with dynamic data-driven workflows was something we proposed to NSF. A couple of rounds of NSF doesn't do this happen. Then suddenly a program emerged with literally writings from those ideas, and Wi-Fi was funded that way. And it was a project that I would tell the fire chiefs, and they would laugh. Literally, you'll never get that data kind of thing, but it was like, we'll raise eyebrows, right? And this is science. It was a truly computer science effort to show this, that we can do that. And what was it at the time is, can we actually get the right model with the right data in real time, make it actionable for fire response? That's how it started. And what's the infrastructure, data systems, workflows that actually helps us do that? That was the work. But over time, it became really useful to fire management, because it was the first example of a fire tech in that sense, in the way we are calling fire tech today. So right now, what it evolved to is, it's an actionable open fire science and AI platform, or program, I should say. And the whole goal is right model, right data, right decision support workflows identified by our partners in the space at the right time, at the right communication. So that's everything we do. And we translate those into products that integrate the science and technology into it. And there are before, during, after, preparedness, mitigation, response, resilience. Those are different applications of all of this. So where are we headed then? We started by wildfire response. We had to, over time, evolve ourselves also in our thinking. How can we build a data infrastructure for the community and do that? And how can we build many versions of this for silos within the community? Beneficial fire, prescribed fire, and other things that helps us to mitigate from the buildup that leads to fire risk. And immersive environments that sometimes get called digital twins, that actually leverage all of that for teaching, communication, design, decision support, and other types of policy making and things like that. So that's sort of where Wi-Fi program is headed now. When we started, as I mentioned, our original goal was initial attack. In the first couple of hours of the fire, can we bring everything together and create a fire model so we can inform? And just to give you a frame of reference, there wasn't a tool to understand where the fire is and where it's going before it went there. Right? That's the main issue at the time, 2008. And to couple all the data together for a fire behavior analyst in a fire department took 4 to 5 hours just to get one model out. So that data system didn't exist. So today we are not just doing initial attack, we are doing extended attack probabilistic models and other types of fire science models to inform other types of decisions. But
you also do cases in which there are not fires, but looking for the probability of fires.
So we don't do risk.
We
Made the decision not to do risk because those systems were available, and they needed, actually, I should say, the way they were available isn't enough. but the science isn't also there to do a state of the possible innovation pathway. Now it's becoming actually possible because some data and modeling advances happen in the meantime. So I think we are in a different time over the last year that risk systems will evolve because insurance needs it, utilities need it, industries are dying because of risk. That's when progress happens.
One is, okay, I get a notice on my phone, it's fire, whatever, weather, don't throw cigarettes into the bushes and things like that.
Yeah.
And during that time, you might actually want, it's almost like weather forecasting for today versus for the next
Correct.
months. So insurances may want to know what the risk that my house burns down in the next 2 years. But if I'm a firefighter, I might want to know, oh, we have fire weather. What's the risk that it will be in the Berkeley Hills? Where should I watch out for it?
And that's exactly why we start with the use-inspired problem. Because we need to understand what we are using it for, and then what kind of science and technology and data sets can be applied to it.
So
Right?
because
That question, without that, what risk are we talking about?
Because if you do it real time, it may be nearer to do it 5 seconds before than doing it 3 months.
Yeah. So that's not the type of workflow or product that we need to build. That's why we need to focus on both the phases of the fire, but also the question we are answering within that phase. Active fire, initial attack, first 3 hours, extended attack 3 to 5 days out. Different applications of data and modeling at detailed levels and probabilistic models versus, quick models to size up that we can influence with data to move them. So those are, for instance, differences, right? And in FireMap, since we started with initial attack, and now it's a part of a California program, $30 million program, we use it as a wraparound service. But also in Colorado, we use FireMap operationally. They use it actually. In that case, we train them and give them. So the idea here is to have 80% of the products, not shrink wrap products like industry style. But then what can we do with partners to actually deploy that last 20% to customize it to that environment? Because there are different models of application in the society too. So those government or fire response processes in different states require different customizations of how this could be useful. So there's a little bit of that social context as well. So, okay, what does this mean? Over time, I used to call them dynamic data-driven workflows. Now I switched over the last 6 months, finally gave up, and we're calling this a digital twin. It's a closing the loop with real-time data. Right? That's a dynamic data-driven nature of this. And what data are we talking about? We are talking about data to characterize the fire environment in this case. Right? And it could be variation of wind, smoke, moisture, fire fuels, the biomass that burn or the houses that burn, fire perimeters, how it's evolving over time, ignitions, and other fire-related effects on the landscape as they are managing it, and active fire and smoke monitoring. These are sort of what can be sensed, what can be guessed. Those becomes the fire environment data. So in this case, fire starts with an ignition. With that ignition, we build fire models. And for those fire models, we need to understand what fuel exists there to burn, and what's the observed and real-time weather. And what can we do with these to inform for the first model? And there's cameras and other things, of course, that go into units and satellites. So the information is coming from, data is coming from different sources. But over time, as we get more perimeters from the fires, aircraft and other, like FireSat is about to happen. They had first readings from that first satellite 0. Then we look at what was the model, what's the measure, and we adjust it. So we are doing very similar things now for human body. Like as people are, the dynamic nature of it becomes the phenomena, how responsive that we can tell something about the nature of someone's condition based on what we know about them now. Metabolomics is a good case for it, for instance. And we do it also for fusion reactor systems. So like this type of approach, before fire, we did it for oil spills. We had drones we would drop in the ocean, which where the Wi-Fi idea came from actually. Then can we do the same thing for fire now, kind of thing. So, but that was the AI until recently. Now AI moved here. The outer shell, the application itself. How do we make user actually interpret what they're seeing through AI, become a part of that? Right? The world is changing in that sense too. And we need a lot of response, good response technologies, but that's only a part of the picture. Small part should be actually. We need to move more into this proactive space. But it's really difficult because proactive means suddenly you don't have perimeters on a map, but you need to understand the risk and you need to understand how to reduce that risk at detailed levels that you wouldn't actually need when the risk is there and you need to act fast. So Burn for 3D came out of that need. The user's fire problem was nation needs more prescribed fire application to reduce flammable vegetation buildup. There are many reasons for that happen. But they need to burn 10 times, 100 times as much in certain locales. But there is no single prescribed fire management tool. The tech models data doesn't exist. They're using wildfire tools to make sure they don't cause chaos. This was when we started in 2018.
Okay, was it mostly kind of domain experts who kind of usual, well,
Yeah.
the person over here has been doing this for 20 years and they're gonna look at a map.
Yeah,
and
these people have great
this,
job
right?
titles, right? They have certifications that are called burn bosses. And burn bosses plan and execute prescribed fire. They are personally liable for what they apply. And they're literally putting risk on the ground. Because they are putting fire to.
Somebody monitor the
Yeah.
pressure.
Yeah, and they turn their experience, they'll burn in a landscape for a while. They turn that into a burn plan. Burn plan has prescriptions of the conditions and also the objectives of what needs to be removed from the environment. To be able to do that, you need to know what's in the environment at a detailed level. And you need to know when you burn it a certain way, will you reach that objective? That experience in that sense wasn't available to science before. I mean, there are scientists modeling at that level, but they take those type of models, took tens of days to actually complete on a supercomputer. There are mechanistic models. What Rod Lynn at the Los Alamos National Lab did is reduce these mechanistic models into models that can now execute in real time. That means 1 hour of fire takes an hour. So it suddenly made it possible around 2018-19 that science that's evolving still while we are building this. Oh, if we can do that, we can actually now use that to plan a prescribed fire. That's the first step, right? This is the model we are talking about compared to this. 30-meter 2D, 1 meter 3D. And you need to understand ignition patterns. You need to understand the fuels at 1 meter scale so that we can actually do even that modeling of many scenarios to create those prescriptions. And now you can understand fire behavior, fuels, consumption, what's being consumed from the environment. But also when you know that, you can compute the emissions and how that transports in the air. And quick fire came out of that because quick is a transport model. So it can compute these emissions and smoke, theoretically. Now it's happening actually, but these are evolving, right? It's an evolving, when we say cutting edge science, that's the cutting edge science here. And then fuels, national average is this. 30-meter pixel with a label. Within that 30-meter tile, there are so many things, and there's just one label about what kind of fuel that is. There's no characteristics, no like other types of density or burn.
And you're doing 1 week.
Yeah.
And the national.
Yeah, so it becomes basically, even in 2D, categorical label. It becomes 2D which is in 2D, it becomes 900 times more detailed, 30 to 1. But then there's this third component, and you can create a baseline through AI and things like that, right? Machine learning. But then we can then do measurements and bring it on top of that to make it more accurate. So that was the idea. For instance, we started in terms of how do we make better fields. And when you have that, suddenly you have the fire model, ignition, you can plan. We had to build an ignition tool. And then you also have, you know, smoke and other things computed. You can start talking about optimization or at that detailed level, making it faster through physics-guided machine learning. You can improve the explainability. So there are lots of opportunities there that we are still not even 10% of the way there, so to say.
So of course, so you say it's now running, what? 8 years ago, it ran as fast as real time, so now probably it runs faster. So at that point, can you dynamically update? So if I plan the fire and now I actually do it, can you then in this model update as it's happening? Say,
If you have enough,
faster than I planned, then I update the model.
yeah, if you have enough models over time, that's what the physics-guided machine learning can do, right? You can look for similar ones, so you can give a risk window at least. Or we have actually labeled risk now on those. We do risk for prescribed fire because we have to. And those ones, we can put like the reason for the risk, because we had burn bosses work with us to sort of say, this is like this, like, so that kind of measurable risk is possible. So we have a demo network that we are running. Actually, we are doing real burns with the tool, right? That's the innovation path they happen. And we have a tool that gets used. So at the
are
usable
these real
stage.
Wildfires, or you could also test them because, you know, they do burns.
Yeah.
To prevent.
Yeah.
Fires, right?
So this is the prescribed
is the
fire
burns
context.
Then
Yeah.
the fires,
Yeah,
yes.
so then what we do now to create is, we actually go to each burn site, which are not wildfire scale, they're small areas.
Yeah.
Then we start collecting data, and then we model it, we create prescriptions from that. But then, you know, orchestration of this, you need to generate fields, you need to generate ignition patterns. And then you model the fire and smoke. Then through this, you optimize. Right? And while we do it, can we use now AI to help us, to help the user of this, who is not coming from a science background, to actually use all data available to them, and also explain and collaborate in themselves to help the user. So that's the agentic AI integration into a tool like this, because it's a completely different model. First of all, we transformed how burn bosses worked. They used to put their prescriptions together and see a wildfire model, if this is really going to cause a disaster. Now they are science-driven, science-based modeling first, creating prescriptions from that, and the day off, they need to check for it. And edge computing and other things are applicable, and we deploy them together as well. So then what data are we talking about here? We talk about the 3D fast fuels characteristics. Like these are, in that sense, voxels, right? They're cubes, volumes instead of pixels. And in it, you have different characteristics. And then they come from LiDAR, ignition applications from edge sensing can be in there, or like we have also scenarios of those. Fire models, model parameters, smoke models. And all of that needs to make sense of through agents that integrate this data with external data sets.
So quick question on the data, the local 3D data, is it just LiDAR, or do you collect, do you do basically additional data collection if you're interested?
We do.
Specific fire, you do extra.
I own LiDAR sensors.
Okay.
It's funny, right? I never thought I would.
You combine LiDAR with hyperspectral, or do you only use LiDAR?
So right now we only do LiDAR, but we have some plant science collaborators who actually are starting to think hyperspectral. So drone-based measurements, for instance, will be applicable for this. So again, technology and science are moving together. And what's the catalyzer to move them together and turn it into a tool before they even knew they could done? So that's the goal here, that we are trying to push the envelope in a direction.
How is this LiDAR?
So Google Maps is a satellite-based one. So you're doing overhead sensing, right? Whereas most of the things, it's useful to understand the canopy, which is the top of the trees. But what you're burning is under the trees. So that's why terrestrial and drone-based sensing, LiDAR especially, is really useful in this context because you can focus on a small area. But that's not the only thing you're using, right? Scientists also plot. They actually literally measure the trees and put them in a, just like a material scientist, they put them in a thing that to understand the vulnerability and density and other things like humidity, moisture, I should say.
My environmental science friends that tell me that essentially each tree has an ID in their model. So is that true for you as well? You know every tree?
I wish. That would be really easy. But in the US, there's also bureaucratic realities. We have Forest Service, we have many different agencies working together, Bureau of Land Management, federal, state, local. So they all have different enterprise systems. So we don't have, in that sense, one agreed upon application archive of how we are actually regenerating. Like when I go to Turkey, they know exactly where they put each seed because there's one central forest management.
Wow.
And they have great data, but then where's the science kind of thing, right? So you can't have your cake and eat it too.
So you used to do multimodal AI long before people were talking about get videos and language into a large language. Whereas this is super
Completely multimodal. Yeah.
So how do you deal with it? How do you make it eventually?
Yes. So this actually shows a little bit of that, right? This is, oh, there you go. This is a LiDAR. This is point cloud when I say LiDAR. So what you're looking at is not a picture. Every point in it comes from a sensor, right? From the sensor. You can take that and put an AI, if you run these as individual services, this is a student code. They turn that into 1, 10, 100,000 hour fields, which means 1 hour means it dries in the right conditions in an hour to become flammable. So that's what you're trying to remove from the environment for the most part, or 10-hour ones. There's what's going on in Canada, that's smoke. They are 1,000-hour fields. They are totally a drought effect. They are different than our California fires. They dry for a long time. They become, again, less fire prone or more resilient a long time. So it takes, those processes are different than our plant processes or vegetation processes. So then you're learning one characteristic to put in that cube out of that AI. And then you can combine that if you put it in the right way, geographic and time, spatial and temporal, everything plays into it. Then you can create a scene, and these are simulation models, like that fire model, because you have the data. Then how do you take that and create an experience like this? This is an avatar, aerial LiDAR. This is like a larger mode, right? And then suddenly the avatar, my video will go into a little bubble. You'll see it once in a while. And there you're also seeing tree metrics. So those are plots that scientists collected in those and terrestrial LiDAR. So it's a lot more centimeter scale at that point, not meter scale. Right, so then this one is good to communicate, both because when you have a prescribed fire application, you don't have to go there. The crew that you're bringing, we can send them something like this. This is a staffer in the Congress. Then we did some there demo last year. And so this is a bubble that's going to be our Christmas party. So, but within that, there's where the fire is being applied. So how do you put those bubbles together so you understand the burn units through measurements, while the rest of it is at still 1 meter area LiDAR or national data that we are trying to create from it. So
you show your fireballs and make the avatar light some grass.
They love it. So like he even did something I'll show later and it became viral between burn busters. I sent it to one in very secret context. not to do that. So, there's the data. Something about data. You need to contextualize it to AI, right? That's what's going on here. And then we render it and create a presentation that's also kind of an AI need that we need to be doing. So for that data system, I need to be here, I think. Again, many types of data is coming, multimodal, as you asked, right? And then more importantly, satellite 30 meter, aerial LiDAR, also 1 meter, let's call it 1 meter, terrestrial LiDAR 1 centimeter. But terrestrial LiDAR gives a way to also monitor before and after. We do this, actually, we had a whole points of panel application that you could see these sites and how the metrics that I showed are evolving.
Sorry, okay, when you say aerial, this is aircraft based?
This is aircraft, it's
Aircraft.
LiDAR, and the geometry of it is different than terrestrial. Like terrestrial sees like this, and then you have an aircraft.
So that's still a bone, or is that literally something more?
It's like 18,000 feet versus the drone would have a different geometry too. And
He's
this one-
asking, how do you collect?
How do you
it?
Oh, okay, this one, you put it on the ground, and then you literally do a 360 scan.
Oh, but that burns
Um,
during your flight.
No,
No, this
he's
is before
doing
and
it
after.
pre and
Yeah,
post,
yeah.
not
But
during.
also
fire.
Yeah, that's true. Nature's good. yeah.
Yes, you could have shown one in the middle during fire, nothing.
You put it there and then move it to the next one. So you can actually measure quite a bit plus in 1 day.
It's a robot or a human?
No, it's just a little device.
No, but he's asking, how do you move it?
There he
So
There
far,
are
you
other
can get
graduates.
robots. Yes, there are undergraduates.
So they're really good. They are actually our partners in Davis. You know, they train the students to do this, but also they're not just undergraduates. For us, they are because we are university. But we combine this with a USGS program called IntelliMont. They actually have a cross-agency Bureau of Land Management, Fish and Wildlife. They have a program to collect LiDAR data. They train real land managers to acquire LiDARs and collect data. So, but what they didn't have is the automated data system that turns those metrics and then can communicate those metrics to systems like this. So we become the last point in their workflow, and we've also managed the data for them and make it openly available to everyone. Right, so there's that where strengths and experience comes in, because they can scale it, we can't. We can just demonstrate it. These type of things are applicable in smoke contexts, right? We say prescribed fires are good, but it's also proven no smoke is good for the human being applying this. What's in that smoke? So there's a lot of opportunity here, but I'm trying to say, but to actually understand the fire environment will take us decades to do it at the levels we imagine we can do. And
Just like Los Angeles.
yeah, and setting up these data systems are really important because of that, right? And data and computing platforms, which is why we do this. But this is only one of the societal areas. And I think everywhere we turn, AgTech, you know, public health, there's a gazillion many examples, that energy, resilience, logging, physiology, these are all actually very similar. These solutions have to have science in them. They won't be unicorns anytime soon, but there's a need. And we need to sort of build the systems to enable the need. And science, of course, you know, big data, Internet of Things, AI, modeling and simulation, this is the space when we say AI in science, right? But it's not just science and methods. The systems I'm talking about is all the rest of it. Federated hubs, knowledge management, DevOps, computing under need, interoperability, explainability, workforce training, culture building. These are the things we need to do today. So in 20 years, we'll have a capable society, right? That's sort of what do we need to enable and what is that enablement layer? And also it's so complicated that we need a full team working on these. one of our biggest challenges is integration in my team, right? When science is evolving, technology is evolving, people are doing things, how do we build it in a way that we don't break things on a regular basis? So full team enabling that integration through integrated platforms. So I see like everyone brings their ropes into it, and then we are trying to create this. Who knows what this is, right? So that's where we are at. So how do we make sense of that? And then how do we then integrate a workflow that looks more like that, not like the knots and spaghetti, right? So what is the system federation, capable services that we can integrate and solutions to integrate those? How do we get there? And we need, of course, AI, but AI needs data. And what are the data systems that enable AI? Because that same field layer, I can enable many solutions with it, but how do we actually repurpose it easily? Or people analyze it so they'll trust the data. So federation knowledge management, what are those general readily available services that broadly we can apply it to teach with it too? And we all know this. Data in repositories, we have bookmarks for those facilities. They give us some services, some input, but it's very limited. So we want our own version to make it really useful. Personal files, I have a lot of LiDAR files being emailed to me. So, and then data ETL services in repositories. There are a lot of unresolved dependencies. When you move it out of there, it's really hard to work with them. It's not a capable service that remotely access. And many more. And then when you self-manage it, you export it, you get maybe some zip or GitHub repositories that you manage, and that becomes a workflow. And that workflow, by the way, needs to be computable on national compute. Lots of dependencies there, right? There's some challenges. You want to send it to your collaborators, hard to replicate. You send a repo, they take 2-3 weeks to replicate it if they have the resources. And then the results. How do we manage and share? You know, when things are out, they are produced at a different place. Right? So fragmented access to data and models, complexity of the way data is managed, disconnect between producing and sharing data, hard to customize, service deployment practices, everyone has their own. In a large team like mine, it took me years to standardize. Right? Everybody built their own engineering solutions at some point. I'm like, no, this is not happening. Right? But what is that platform? It's not like we can change it right away. Specialized compute readiness, more and more with AI, we need more specialized things. And this is my favorite because we need to teach on research infrastructure. We can't disconnect research and education at this point, and we need to teach with research data. Not possible in today's, I mean, there are some good things that happened over the last couple of years. And then we don't focus on user experiences. Users are moving out, right? They are not scientists who are, they still exist. We have user experiences for them. Let's focus on the more people who are we are trying to bring into the AI space, because we built a whole user experience for very capable computing people.
One of the things is that, oh, you should send this data and sort of, why do that at all? Why doesn't it just live in the cloud and they can sort of log into your cloud? Why would you ship them that?
Yeah, so it has to live in the cloud, but most of the time, the users who are coming in now, they don't know how to use the cloud, or they don't have storage. Data is not like compute either, right? You store it in the cloud. And if you're NASA and NOAA even, you store it in the cloud, you give it to your users, you're hit with egress charges. True story, right? So there is no model for us to actually help even the facilities themselves to get out of this egress charge mode. I think we think we have a solution. That's why I'm saying it. So this is the AI integration everywhere, and data is everywhere, as you said, in the cloud, in on-prem, small data, big data, doesn't matter. How do we build a data platform for this? That's where we started with the National Data Platform, but also in a way that you can create those solutions I was talking about initially. And also architect for it, involve diverse users, identify what is the gap between research and education, infrastructure and needs. And then in a way that brings an ecosystem approach, service-oriented approach, so we can do capability integration. So those are the data gaps that we wanted to at least focus on this. So 2 years ago, we were funded to do the National Data Platform as a pilot. And the big thing about the National Data Platform is distributed in design, and it's all service-based. We focus on usability, interoperability, and composability. Those are the 3 principles. We don't have storage, we don't have compute, other than some transitional. We build on existing stacks, and we don't build middleware stack. So the idea is usability comes through user experiences within a centralized hub, education hub example I'd love to emphasize later. And then we build a federated stack that standardizes anything that's built near data, like let's say in the cloud, through building experiences next to data or compute or whatever that special service need is. And when we integrate all these, we integrate those not as data set, but as services. So it's a federated catalog of everything. You can think of it that way. And that federated catalog, how do we replace this with that? You can discover things in that catalog, data model services. If they are not there, or if you have yours, you catalog it through ingestion pipelines. Or if you have a lot of data like a facility and you have researchers and developers, you build an endpoint set of services. Or if you're actually an external person, you're trying to customize facility data like NASA NOAA data included for your own community to specialize it. You then create an endpoint for your community and build those services next to the data in a way that integrates with the rest of the catalog. So that's the basic composability extension idea. Then in NDP, usability comes from these workspaces. You start collecting those things into those workspaces. If you're individually working, you deploy those workspaces are launchable on national compute. And then you can store on national storage through standardized experiences. And by the way, if you want to collaborate, because we all collaborate in these modes, you can actually carry that workspace into a collab studio with shared users and storage and compute behind it. So you can reproduce what your colleagues are doing and also add to it. So that's the whole flow. And I knew I won't have time for these slides, but I want to emphasize a few things over it. The idea here is we started with a needs assessment. Since we are understanding usability, interoperability, and composability needs, we do a needs assessment with different communities. That could be faculty for the education hub or data challenge providers for informal student training. And of course, there are users in different science environments. And then we do an application co-design. And everything in the co-design gets turned into a training module, so that we do capacity building for the users through it. So that's the pilot application of NDP. Current users are researchers, researcher educators, data providers and stewards, student learners, and research software engineers. Those are the users in the pilot we focused on. There's a whole flow of things. I'll share the slides. I'm gonna just quickly, discovery happens in text, conceptual, map-based, spatiotemporal, and conceptual mode. And we are adding through Julia Lane's democratized data services, the usage analysis of the data. So it's combining the agents that come from there with the rest of the data search capability. So data can be integrated with insights that are gained through data. So value of it over time, we can dashboard and analyze through the system. And especially conceptual search opens the room for conversational search. So that's actually, we are getting rid of a bunch of search capabilities just to switch to conversational search. So that's what's happening. Catalog, there's a whole ingestion process, and we try to crosswalk many metadata to a standardized context. And we also, if the data is in national, the data delivery platforms like open source data federation, we add those namespaces behind the data. So when we carry them to a Jupyter Hub, the workspace, it fetches automatically from the nearest cache. So some of the large volume data delivery problem gets solved that way. Some examples of those and endpoint deployment. These endpoints, again, we are imagining the first use of it will be for facilities. When you have large data, NASA's, NOAA's, your Earth scope is the main example here, but they are deployable anywhere. And then even on Amazon, we have some deployed because NASA, NOAA, Earth scope data, they're all on actually AWS. So what happens here is this endpoint works on Earth scope data and streaming data from Earth scope. What it does there, it archives it on OSDF in a way that makes it available as a historical context to the NDP catalog, but the streaming service that or other types of ways to work with this data becomes then available through those services to NDP. So one can carry them to their workspace. Right? That's the facility context there.
Question, a lot of things that happen on the hub, but the data is sitting on S3 buckets that are on the AWS side. What did you do with the whole?
So that's the needs assessment work we are doing actually in terms of cost analysis. What would that be and how do you federate that, right? One of the things is compute right there and you're getting very little results back. And that's the main mode we worked on so far. But yeah, if there's a lot of movement, like what moves to OSDF is a certain snapshot here, right? So data is managed and searched through it. So we have those data sets and accessible in NDP. So that's minimal. But the full archive and how do you move it, you shouldn't. I think at that point the answer is, yeah. Because the compute is free for most of the government ones. And then workspaces, as I mentioned, you collect things in. If you have Hugging Face data and models that, you can integrate them into NDP and run them through your workspace. This is sort of deployed on NRP, the National Research Platform that some of you hopefully use, is a GPU cloud or cloud of resources, distributed resources. These workspaces actually mostly launch on that. So there's a launch piece, the spawner, that's somewhere in here probably. So we are picking resources on the National Data Platform. And then what launches there as a service is the workspace, that the Jupyter widget, so to say, that integrates the workspace and all the resources in it to the compute environment. And we can do it on Amazon or on-prem resources. Not on, like we are working on some ways to do it on more HPC resources, but that's going to be kind of less obvious how to do it, unless we just run it and wait, which is the current mode anyway. So we are using the same approach for the education hub. And I would love for you to provide educational resources or try it out with us. We can work with you on that. This won the best paper or best paper at the PERC because I think it's like the first time something like this is demonstrated, right? The education infrastructure being research infrastructure being used in classrooms. Something we've done was Amarnath Gupta's class. And here, each student, this was a graph analysis course. Each student worked with 40 gigabytes of data, which is not a lot, but they can't do it on their laptops. It's difficult to do otherwise. And NDP, in this case, managed to administer some of the databases in containers. So we are trying to understand what would that mean to scale that and what's the support model for it. And then this one is my favorite, and I'm gonna quickly pass after this to the end. This is a data challenge we ran. Interoperability, data comes from Forest Service inventories, LiDAR scans, and everything else, and it goes into a parallel. And workspaces are built as sprints, and each sprint leads to a Next one, like it teaches something, right? It teaches scalable computing, it teaches about data sets, it shows some examples. So students learn through this space within those reproducible workspaces. They team up, by the way, on the platform. They create teams. And then the last question is the challenge question, this sprint. So they then work together on the NRP through the workspace and then submit their solutions to NDP, the whole workspace to NDP. And the judges reproduce and execute their work on the NRP. Right. And it was the first time we were doing it. We advertised it to UCSD students. We built actually an onboarding module you can take when you go to NDP. And then we thought we were doing it with UCSD students. Students from 8 other colleges and universities found it, self-onboarded it, and they showed up. And we're like, we didn't even know they were here, right? So this is a way to, I think, and now the winning solution is a learning module in the onboarding module in NDP, right? So that's the future of this. So how does it help wildland fire? Burn for 3D, all the data, those simulations going to OSDF, coming into an NDP catalog. So AIs could be built on top of those. Those agents can be built in NDP. Similarly, any data set, any service, we are building a digital twin factory. So you can actually integrate that digital twin backend workflow through existing data by bringing and integrating your own immersive forest. What runs behind is an NDP endpoint. So I can bring my workspace and expose it to the endpoints. I can bring new data into the immersive environment. And then Wildfire Science and Technology Commons, CNDPs means custom branded NDPs. So the whole NDP is a shell over it. So Wildfire Science and Technology Commons is, for instance, a CNDP. It has its own logic. It's built for fire tech enablement with data and all those data systems. So the Fireforge platform on it is actually NDP. It uses the core services of NDP, and we have, right now we are switching to a custom, the headless CMS, so you can actually build this on your own. We have about 10 CNDPs at this point. And remember, I was saying the 3 metrics are generated. This is actually the LiDAR scan. You were asking how it's generated. It's like 360, and somewhere here is the sensor. And for each of these sites, we generate a metric show up in this application called plot to panel, points to panel. And each frame in this is processed. So processing of it is bringing that LiDAR data into a workspace and then adding Isaac, my PhD student script. This is Letitia in our lab. And then collaborating with collaborators through it. And then when you actually create that, first of all, you prepare your data sets. You collect them into a curated catalog because you can use it time after time. And here, she's now registering those data sets into her curated catalog. And then after this, she's going to create a workspace that has those data sets in it. Within that workspace, she actually built it here, right? She added the data sets, she added a GitHub repository to it. Then she adds a project to share with collaborators. I'm gonna move on a little bit. Here, she's adding a group to share it with. And now tutor and UCSD demo account is in there. And then she's now adding that workspace into that collaborative studio. Now what she does is she goes to that workspace. Oops. And she's gonna launch that collaborative project, that workspace in it on the Jupyter Hub. She asks the resources she wants from NRP. And then it opens it up, let's say. And then the next step will be the hub, Then she's going to execute it through that. She actually GitHub gets cloned here, workspace gets cloned here. And the last step is then she saves that back to OSDF. So that whole flow I showed, this example shows all the flow that I demonstrated before. So this is the last slide, actually, because what I tried to demonstrate is that infinite loop and how we tried, at least we are still building an infrastructure to enable that whole loop from multi-vector perspective. So all the collaborators here, they use it because they can have the data systems now integrated to their platforms. They can work with the developers and generate those data and services deployable to their tools. And I think this is the type of ecosystem we'd love to build. And if you have things that look like this, especially class materials and data challenges, but research projects too, of course, or data sets, please contact me. And I'm ready and available here also to talk about it. And I apologize, I went over.
Okay.
Thank you.
Yeah, we have time for maybe a handful of questions, and then Ilkay also has some time in the afternoon,
Yeah.
I understand. So I highly encourage you to meet with her if you want to.
Yeah, it's more kind of like I want to say thank you for what you've done here because, you know, my family lives in zones, these fire zones. We use this like almost every day.
Wow.
And it's integrated into some other like simple apps for using on their phone. One of them is called like Watch Duty.
Yeah.
And where they're able to track the fire, they're getting these emergency alerts, right? That you would never get because nobody has landlines anymore, right? And so they're able to decide like based on their own data, like when they're gonna have to evacuate, which one to. And so like this is a very important tool for not just the fire people, but for the people that live in this area.
Yeah, that's an excellent example of how these things can move into the future, right? And the universities, I think our goal is to demonstrate it and enable the innovators like that to actually take it to the scale level that the society needs. And I think WatchDuty won like the best app of the year or something in Apple, right? In the category of they're in. So, and that's a great example because we had the public hitting our servers for a long time. And I should say we had venture capital also knocking on the door to do similar things, but we are at the university. And, you know, building an app is not I mean, we would love that problem, right? But the idea is this enables us to do what we do best and then creates a model for innovators or entrepreneurs like WatchDuty and others building fire tech with what is ready to take it and scale it. So it also creates actually an economy or public impact of different sorts. And Wi-Fi isn't the only one, right? Who caused like which enabled WatchDuty. There's the camera networks, there's satellite, there's all kinds of things. But I think we need to create this open science and sharing environment in ways that helps us sustain these things too. Like that's the next step in the commons. That's what we are trying to do. We are working on a marketplace around open things. That's not a monetary marketplace. It's a sustainability marketplace. And like there's some rules of engagement around it. And you know, if something is being valuable, how do you make sure that value also gets back to the scientists, modelers who are working on it, because those models are now being used, but there should be something around that, right? A model, are we able to gonna build that is the question, but.
One thing I would risk, the easiest way to get rid of risk is cut down all the trees. So a fire. So when you're working on that, I mean, both for like insurance companies and for you know, the government, which you also may work with in the future is the private forestry industry, right? Because there's a lot of people may not know we have a ton of forest that's accessible to us. But just when you're working on the risk portion, I would just say be careful to not expand it too much to where we start ruining like the natural,
Yeah.
beauty of the forest. Because I've been to
Mhm.
dry burns and things like that. And, some of them, they don't look as great after we take away trees. So I guess I'd just say be wary on the external pressures to like, the insurance companies, they want to
Mhm.
cut down everything within 200 feet of a house.
Yeah.
Which is like, well, then you don't want one house in the city and not a house in the forest, right? So,
Yeah.
but just be aware of those like external pressures.
Yeah, and it's like a system of systems, not like it is, right? And for instance, why do we need to build it as a commons approach? Let's say in California, we have metrics for the landscape, its health and resilience, and they get turned into 19 different agents. We built it actually for California, right? That data comes in and becomes an accessible data set. We also have information on vegetation treatments. Those are open things that can be integrated through also with like risk planning efforts. Where is the biggest risk? And where the application of prescribed fire, there are optimization tools that are happening. There are various, both fire tech and open examples of those. So when you put all of this together, and also there's a WUI, the commons is happening for the WUI, you suddenly have more of the data you need to make that type of trade-off decisions, right? How do you actually reduce the risk without ruining the environment or a neighborhood's vitality or people's sense of place? There's all a part of this whole picture. And right now, I mean, it's improving through these integration approaches. We don't have those things in shapes that are integratable or even discoverable. People don't know that exists. So in the commons, one thing we are trying to do is actually make private things discoverable. Right? If it's not open, but you want people to find it and have that conversation with you, that should be discoverable. Right? But discoverability is different than openness. So we are trying to bring that concept to be the core in NDP too. Right? At least the metadata should be discoverable. So you have a point of contact and like place, you know how to get it. Otherwise, it's really complex. It's a wicked problem for a reason, I think. And those data sets and silos, yeah, it's going to take some time to get there, but I think we will. And Google's and other things like at that scale are interested too, right? There are scale partners here that we can think through. Yes. Huh.
I'm telling you, like,
I feel like a celebrity now.
And then, have you guys thought about integrating work with CAL FIRE, like their resources that they're throwing on a fire, how they can decide planes and dozers and stuff that they're supposed to put on a specific size? I mean, they know by history, but obviously the more info that you have.
Mm-hmm. Yes. I think it's an industry that things happened the way they were for a while, right? There are some healthy bureaucracies, let's put it that way. So the culture is changing. You know, what can be opened up, what is not, you know, who shares the information. You know, maybe pendulum swung a little too much on model sharing also, for instance, in the Bosch duty, right? You know, in my opinion, models are not informative for the public. They are for the trained eye, right? So how do you turn that into interpretable bits? Or like, how do you make sure they are used in the right way? So I think those are the healthy bureaucracies I'm talking about. They are very actionable the way they are being used at their source. And how do you make them responsibly actionable in other contexts, especially when we're opening them up? So there are some things that are open like that. There are some things that are not yet, because that's the conversation at the state level or CAL FIRE and other places that's going on. Because it's also kind of, fire is already a chaos, right? And adding more things to it, what can it do socially in that environment before and after too? And like, can we do it without harming something else, right? That's why I think they're being pretty careful about sharing some of that. Yeah.
Let's thank you.
Thank you.